Hey guys, welcome back to another lecture video for Chem 115. In the previous lecture video, I discussed the idea of entropy, which explains why a system will move toward a specific final equilibrium state if its initial equilibrium state was disturbed. Now, this explanation is based on the idea of the most probable outcome, such that according to statistical mechanics, if more equivalent microstates can be achieved in the final state, then it is more likely that we will find a system that will transition toward that state. Okay? And so once again, entropy is a numbers game. Now, this phenomenon can be further explained and can be observed by looking at this diagram that I drew. On the left-hand side of the arrow, here we have this container containing 9 purple molecules, whatever these molecules are. And so this is representing the initial state of the system. If I were to disturb the initial state, such as removing the barrier, what is the most likely outcome that will occur once that barrier has been removed? What is the possibility, or what is the probability that all 9 of those molecules, these purple molecules, will stay on the same side as where they were at in the initial state? And what is the probability for those 9 molecules to explore the entire volume of the container? Okay? So that's what entropy is trying to describe, right? And since it is more probable for those 9 molecules to explore the entire volume of the container, then it is to be expected that the system will transition to that state. Now, in this lecture video, we will see how we can quantify entropy instead of predicting if it will increase or decrease during the course of a chemical reaction. And so before we learn how to tabulate this esoteric idea called entropy, we need to talk about the third law of thermodynamics, because it really sets the precedence for us to be able to calculate entropy. And so let's go ahead and go through it. So the third law of thermodynamics states that at absolute 0 Kelvin, the entropy of a perfectly ordered, pure crystalline substance is 0. And so, in short, when the temperature of the system is 0 Kelvin, it is expected that the entropy is equal to 0. Okay? And so, why is 0 Kelvin known as absolute 0? And why is this so special with respect to entropy? And so for us to understand this concept, we need to take a look at our units that describe the average kinetic energy of a system, which is typically known as temperature. And so if we're looking at our 3 units for temperature, here we have degrees Fahrenheit, degrees Celsius, and finally we have Kelvin. Now, if you guys have visited New York or some type of state up in the north during winter, you guys are familiar with the idea of degrees Fahrenheit and or degrees Celsius being expressed in the negative values. So these two temperature units can have a negative value for both degrees Fahrenheit and degrees Celsius. And so if you were to visit those states up in the north during the winter, when the temperature gets to, for example, like -5 degrees or -10 degrees, it's not as if everything has stopped moving. And so you can still see on the street, some form of motion, albeit it's very, 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 very slow, or it almost looks solid, right? However, in the molecular level, when the temperature is negative degrees Fahrenheit or negative degrees Celsius, at an atomic level, those molecules, even though it looks crystalline or solid to us by the naked eye, they still have some type of motion. They still have some type of rotation or vibration, maybe not so much translation. And so, since there is molecular motion at negative degrees Fahrenheit and negative degrees Celsius, that's not going to be our absolute zero. When you guys are looking at the Kelvin unit, it turns out that the lowest value that the Kelvin unit has is 0. And so if a system were to approach or is at 0 Kelvin on an atomic level, there is, if it's approaching 0, there's very, very little molecular motions, very little rotation, very little vibration, etc. But when you are at 0 Kelvin, there is no molecular motion at all. There's no atomic rotation. There's no atomic vibration. Everything is just at a standstill, which is kind of creepy. And so, because at 0 Kelvin, it's been theorized that there is no atomic motion, vibration, translation, rotation, what have you. The entropy of that system is going to be 0. Okay. So that's what the third law of thermodynamics is telling us. Now, how can we use the third law of thermodynamics to our advantage in terms of quantifying entropy? Well, we can go ahead and look at the converse. If the temperature is greater than 0 Kelvin, then that means that the entropy of the system is greater than 0. So in other words, the third law of thermodynamics gives us this reference point to calculate the entropy of a system from, right? And so we can go ahead and expand this concept and talk about standard entropy. And by standardizing these values, we're giving very specific conditions to, like, for example, like all scientists, right? And so if a scientist wanted to calculate the entropy of a specific substance, then for it to have more of a universal effect, if you will, it must follow very specific conditions. For example, you must have 1 mole of that substance, and it needs to be at 298 Kelvin or 25 degrees Celsius under 1 atmospheric pressure. And so the idea of standardizing this entropy value will enable researchers to obtain a higher level of precision if all of those numbers were calculated under these specific conditions. And so going back to the idea of the third law of thermodynamics, the standard entropy is going to reflect a value from warming the substance from 0 Kelvin to 298 or 25 degrees Celsius. So we're using this idea of the third law of thermodynamics to kind of give us like this reference point for us to measure to and from, or from and to. Another item that we do need to take in consideration is elements in their standard states. So what happens, what is the entropy of pure substances? And so if you recall from thermochemistry, for pure substances, as well as our diatomic gases, the enthalpy, the change in enthalpy is zero. Okay? And so, I'm sorry, the enthalpy of formation is equal to zero. Now, what this is telling us is that if we're trying to create, for example, O2, well, there's no reason for us to form O2 because it's a naturally occurring substance. And so therefore, its heat of formation is equal to zero. However, under the perspective of entropy, entropy can also look at the ability for that substance to achieve its specific microstates. And so all pure substance have the ability to achieve these different microstates. And so therefore, for pure elements such as pure copper, pure gold, pure sodium, and our diatomic gases, Hofbrinkel, H2 gas, O2 gas, fluorine gas, bromine gas, iodine, nitrogen gas, and chlorine gas, their entropy is not equal to zero, okay? Because all of these elements in their standard states, meaning that it's at 25 degrees Celsius, meaning that it is above 0 Kelvin, that's telling us that they must have an entropy value to them. Okay? They're in constant motion. They are in motion, even though they're not reacting with another substance. And that the fact that they are in motion tells us they have some type of entropy to there's some type of value with respect to their entropy. Okay. And so an example of pure metals would be like I said again, like pure silver. And typically in a chemical reaction, you would only see one of that substance with no with no anion, and the physical state of matter is typically solid. And so I guess we can kind of broaden what a pure metal would be depicted in a chemical equation, and that would simply be like X representing the metal, and having this solid state. And the fact that there is no anion or polyatomic attached to this metal. All right, cool. And so let's talk about the units for entropy, standard entropy. And so our units is going to be joules per mole Kelvin. And so the fact that our standard entropy is dictating very specific units, that informs us that when we're doing these problems, we need to make sure that all of these values are in joules, all of these values are in moles, all of these values are in Kelvin units. And if they're not, we would have to perform some type of conversion so that those values reflect the proper units of entropy. And so what I want to discuss next is calculating the standard entropy change. And so whenever you're putting, this delta, remember this delta is representing final minus initial. And so what you're conveying to the reader is that there is a thermodynamic process that's happening. And what you're trying to convey to the reader is the overall change in that thermodynamic process. And so looking at this chemical reaction, each of these substances have a finite standard entropy value. And so to describe the change in entropy as we go from reactants to products, we can go ahead and use a form of Hess's law to simply determine the total entropy in the final state and subtract that from the total entropy of the initial state. And so the equation that we're going to be using is this. And this is very, very similar to Hess's law that you guys learned in the first semester of general chemistry. And so I'm just going to go ahead and copy this real quick, or I'm just going to copy this. And I'm going to go ahead and paste it here on the side. And so what you guys are used to seeing from first semester of general chemistry is this equation in the perspective of enthalpy. Whereas if you guys are trying to calculate the heat of the reaction, reaction is abbreviated as RXN, then you guys are using the standard enthalpy value for the products. Typically, it's a heat of formation value. So let me see if I can just move this here. Okay. And so you guys can determine the heat of your reaction under standard conditions if you guys take the product of the heat of formation of the product times that by the number of moles, which is the coefficient in your balanced chemical equation. And you guys are just going to add all of that up for the products. And the same idea goes for the reactants. You guys are going to multiply the number of moles to the heat of formation value, and then you guys are going to add all of that up. And at the very end, you guys are going to subtract the sum of your products and the result of the sum of your reactants. So in a similar fashion, you guys are going to apply this modified version of Hess's law to determine the standard entropy change of the system. And the standard entropy change of the system will give us an idea as to overall, determine whether or not there was a net increase or a net decrease in entropy as the reactants gets converted into product. All right, so we're going to go ahead and apply this formula by going through a couple of examples. And so here we have calcium carbonate, and it looks like there's a decomposition reaction occurring, producing carbon dioxide and calcium oxide. Now, if you guys are looking at this chemical equation, we always want to make sure that it's balanced. And so here we have one calcium, one carbon, so those checks off. And then here we have 3 oxygen. Here I have 2 oxygen. Well, that 3 is not equal to 2, but remember that we have another oxygen on the same side, on the product side. So therefore, we have a total of 3 oxygens on the product side, which equals to the number of oxygens on the reactant side. And so it looks like we have a 1:1:1 ratio between reactants to products. And so if we weren't trying to calculate the standard entropy change, and if we're just like looking at this chemical reaction and we're trying to predict whether or not entropy will overall increase or decrease as reactants gets converted from reactants to products, what would it be? Would we get a net increase in entropy? Would we get a net decrease in entropy? How do we answer that question? And so if you guys recall from the previous lecture video, there's a couple ways that we can tackle this. One, we can look at the change in the number of moles or change in the number of our coefficients between products and reactants. Number two, looking at the physical states of matter. And so if I'm just looking at the numbers, notice that on the product side, I have a total of 2 moles of particles on my product side. And here I just have 1 mole of particles on my reactant side. And so if I were to take the difference between the two, and remember that the difference is always final minus initial or products minus reactants. So it's going to be 2 minus 1. That's going to give us a positive number. And so since our n value is greater than 0, then that's telling us that we overall will get an increase in entropy as reactants is being converted to products. So that's what we kind of went through in the last lecture video. Okay. And so what we're going to do is we are going to, oh, and also before I move on, we can also take a look at the physical states of matter. And so for example, here, this is solid, gas, and solid. We're going from solid and we're producing gas molecules. And remember, gas molecules, they have higher entropy than molecules that are solid in state. They have greater flexibility to explore all of these different equivalent microstates that would result in a higher entropy of the system. And so overall, we can go ahead and conclude that there should be a net increase in entropy as reactants gets converted to product. And so what we're going to do is we're going to take this concept one step further, and we're going to quantify it, right? And we kind of quantified it relatively by looking at the coefficients in the balanced chemical equation, but I guess for us scientists it's not enough, because we need to be able to tabulate the change in standard entropy, so that way we can do something else with it. And that application will be discussed in a lecture video, in the next lecture video. So let's go ahead and look at what we're working with here. So we have calcium carbonate decomposing to carbon dioxide and calcium oxide. To use this formula to determine the change in entropy, in standard entropy, we're going to have to add up all of our products after they've been multiplied by their coefficient and subtract that from their reactants after those reactants have been multiplied by its coefficient. Okay. And so I think I might need more room for the products. Okay. And so looking at the product side, we have carbon dioxide and calcium oxide. And notice that I gave you guys the entropy values for these substances. Now, if I do not give you guys your entropy values for these substances, then you need to use the reference that I will post on Canvas and search for the entropy values using that reference sheet. And when you guys are using that reference sheet, very similar to your heat of formation values, you have to pay attention to the physical state of matter, not only the identity of the substance. And so, for example, the entropy of water in liquid form is different than the entropy of water in gaseous form. I mean, they're both H2O, but one is in solid phase, one is in gas phase. And the same thing can be said in liquid phase. Like all three of those water molecules, or all three of those physical states of matter for water, will have different entropy values. So you definitely want to pay attention to the physical states of matter and make sure that you guys are using the right one. And so I'm going to go ahead and represent 1 CO2 here, and I'm going to go ahead and represent 1 CaO here. And so these are my products. I'm just going to erase that for now. And so what I'm going to do is merely substitute this the identity of the substance with the number that it represents. And so I'm going to bring down the 1. So here I have 1 parentheses, and CO2 is 213.74. So I'm going to put 213.74. Then this is going to be joules, moles, Kelvin. Okay. Now remember, very similar to a problem that we did in one of the earlier lecture videos, that 1, the coefficient, has an invisible unit of moles. And so what you're going to do is you're going to, when you multiply this, you're going to cancel out the mole unit. And this leaves us with just 213.74 joules per Kelvin. Okay. And so I'm going to move this guy over just to make sure I have enough space. And once again, I'm going to put that 1 mole in the very front, and I'm simply going to substitute calcium oxide with its value, which is 38.2. So this is going to be parentheses 38.2 joules per mole Kelvin. Now if I were to multiply these two values, I'm going to bring down this plus sign. I'm going to get the same value, which is in this case 38.2 joules per mole Kelvin. Oops, not per mole Kelvin, just Kelvin. Okay. And so both of these two values are still my products. And when I add these two together, let me just do that right now on my calculator, I'll get, so 213.74 plus 38.2, that's going to give me 215. Now, since we're adding, we have to, keep track of our sig figs. So here, this is the least number of places after the decimal. Remember, we're applying the rules of addition. And so if I want to be precise with my values, it's going to be 251.9. Okay, so I'll go ahead and add that last digit, that 4, just for accuracy, but I'm going to put that mark at the very top to represent the precision for my sig figs. All right, so now that I have my products, I'm going to go ahead and look at my reactants. And so my reactants is calcium carbonate. And so I'm going to put calcium carbonate here, and then I'm going to carry over that coefficient of 1 to represent the fact that there's 1 mole of calcium carbonate. And I'm going to go ahead and replace that chemical formula with the value, the entropy value, which is 92.9. And so here I just have 1 mole times this by 92.9 joules mole Kelvin. Okay, and I'll just go ahead and bring that minus sign down just to be consistent. Moles will cancel. If I multiply, then I simply get, oops. Let's see here, minus 92.9 joules per Kelvin. Yeah. And so in terms of sig figs, your coefficients are going to be in exact numbers. According to the balanced chemical equation, you have exactly 1 mole of calcium carbonate, exactly 1 mole of carbon dioxide, exactly 1 mole of calcium oxide. All right, so after I multiply those two values, I'm just going to go ahead and bring them together. So I'm going to scoot this over down here. And so once again, looking at the sig figs, remember now I'm performing rules of subtraction, which is same as the rules of addition. It's just the least number of places after the decimal. So I'm going to go ahead and subtract 92.9. And the value that I'm going to get is going to be 159.0 to the correct number of sig figs. And this is joules per Kelvin. And so I didn't bring down my units, so I'll just go ahead and move that just a little bit. So let me move this, so that way I can bring down my units from the addition. Okay, so if I'm adding these two, then joule per Kelvin plus joule per Kelvin is equal to joule per Kelvin. So we're just combining them. Cool. And so this is telling us the overall change of entropy at standard conditions. And so in the perspective of energy, we have a positive value for entropy. And so since we have a positive value for the change in entropy, then this is telling us that as we go from reactants to products, the entropy of the system will increase, which is what we predicted at the very start, right? We predicted at the very start, based on looking at the number of moles in the physical states of matter, that yeah, we are going to get an overall increase in entropy as we go from reactants to products. And now we've taken it one step further and used the standard entropy values to further corroborate this conclusion that we've made prior to the start of this calculation. All right, so hopefully you guys understood how I kind of pieced all of this together. We're going to go ahead and do one more example, very similar to what we did in the recent example that we just completed. And so here we're going to predict if the entropy of the system will increase or decrease. Then we're going to justify our answer by calculating the change in entropy. And so to predict if the entropy of the system will increase or decrease, so I'm going to just look at this part right here. Okay, I have two options. I can look at I can look at the difference in the coefficients of the products and the reactants, and I can go ahead and look at the physical states of matter, the transformation of the physical states of matter. So let's go ahead and look at our coefficients first. So this equation has already been balanced. I already balanced this equation for you, and so I'm just writing in pink the invisible values, the invisible coefficients. All right, so let's see here. To predict the entropy of the system, if it's going to increase or decrease, what we want to do is we want to calculate the change in the coefficient between products and reactants. And so here we have overall 5 moles. And here we have overall 4 moles. And so if we do 5 minus 4, or products minus reactants, that's going to give us a value of positive 1. And so since n is greater than 0, therefore the entropy is going to increase. Okay. And so as we go from reactants to products, the entropy is predicted to increase. Now let's go ahead and take a look at the physical states of matter and see if we can form some type of prediction by looking at it. So here we have solid, here we have gas, here we have solid, here we have gas. So without looking at the actual coefficients, without looking at the numbers, the fact that we have solid gas, just strictly looking at the physical states of matter, it's nothing conclusive, right? However, by looking at the coefficients, by looking at the numbers, we can see that we probably will produce more particles. So 5 moles has more particles, and 4 is a lesser number than 5, so we're going from something that we have less particles to more particles. And so that's why we're taking the difference in the number of moles to determine the number of particles. And the idea is that if we have more particles in our products, in the result, then therefore the entropy is expected to increase. Just because, like what you guys kind of saw in the previous lecture video, if I went from 2 gases to 4 gases to 10 gas molecules, there's more macro states, which is representative of the number of black boxes that I drew. And each of those macrostates has, an increasing number of microstates, these overlapping combinations that would produce that specific macrostate. All right. And so now that we've done our prediction, we're going to go ahead and justify our answer by calculating the change in entropy, change in standard entropy. And so once again, we can go ahead and use these given values, these standard entropy values, to calculate the change in standard entropy. And so by calculating the change in standard entropy, we can go ahead and gain some idea of the thermodynamic process that occurred. And so to calculate that, we're going to take delta S. It's going to be sum n times S of the products minus so once again, we're doing products minus reactants, and we're taking into consideration the number of moles, which is the coefficient in the balanced chemical equation, in addition to the standard entropy value that's already given to us. And combining all of this stuff, adding, multiplying, subtracting, it will give us the change in the standard entropy. And so our products in this case is going to be, let me see if I can highlight. So it's going to be aluminum, and it's going to be water in gaseous form. And so here we have 2 moles of aluminum, and then we're going to multiply that by the value for aluminum, which is going to be 28.33. Oops. Joules per mole times Kelvin. Now, it looks like we do have a second product, which is water. And so that's what I'm going to do next. I'm going to add that to 3 moles, because I have 3 moles of water, according to my balanced chemical equation. And I'm going to look at my entropy data for water and notice that it's gaseous in state. So make sure that your physical states of matter match up. Remember, water has different physical states of matter, has 3 different physical states of matter, and their entropy values are going to be different. So this is going to be 3 moles times that by 188.825, and this is going to be joules, mole, Kelvin. Oops. And so I'm going to go ahead and put a super parentheses around this because this is just referring to the products. And so I'm going to go ahead and move this part over to represent my reactants. So I'm going to put that minus sign, another super parentheses. And so my reactants, I have two. I have aluminum oxide and I have hydrogen gas. So I have 1 mole of aluminum oxide, and that is 50.92 according to my value. So this is 50.92 joules mole times Kelvin. And then I'm going to go ahead and add that to 3 moles of hydrogen gas, and my value for hydrogen gas is 130.684. So this is going to be 3 moles times 130.684 joules mole Kelvin. Okay. And so now I've represented all of my reactants here. And so all I need to do is just multiply everything across, make sure my mole unit cancels, and really just reduce what I have. I mean, if you guys want, you guys can plug it all in one go in your calculator if you know how to manipulate your parentheses in your calculator. If you don't, then I suggest you guys do this piece by piece and then just put everything together. And so keep in mind your rules of sig figs. We're working with addition, subtraction, and multiplication. And so here I have 2 times 28.33. So this 2 is an exact number. And so I'm just going to report all 4 sig figs. So here I have 56.66. And I'm going to put a little mark above. And I'm going to go ahead and move on to the next one. So this one cancels. So I have, 3 times 188.825. And so here I have 566.475. I'm going to put a little mark above there. And then I'm going to go ahead and perform this operation. So this times this, it's going to be same value, so 50.92 joules per Kelvin, plus this cancels. And this is going to be 3 times 130.684. That's going to be 392.052 joules Kelvin. All right. And so now that we've reduced each term, we're going to go ahead and just combine them. And so I'll go ahead and do the products first. Oops. And so here I have 56.66 plus 566.475. So I need to report 2 places after the decimal because that's my least number of places after my decimal. Here, this number has 3 places after the decimal. So since I have 2 dp, whereas this is 3 dp decimal places, 2 decimal places is my lowest. And so here in this case, I'll get 623.14. I'm rounding that up to the correct decimal place. Well, actually, we're not done with the problem just yet. So let me write the full answer. So 623.135. And I'm going to put a mark above the 3. And so next one is 50.92 plus 392. 0.052. Once again, 2 decimal places, 3 decimal places. So I need to report 2 sig figs, or 2 decimal places, I apologize. So that's going to be 442.972. Joules Kelvin. And I'm going to put a mark at the top just to remind me. And so once again, I'm not trying to round as I'm going along. I know in some of my lecture videos I've rounded as I went along. It really doesn't change your answer too much. I'm just trying to be a little bit more precise in my work since I'm a little bit more conscious of it. So if I combine these two values, so 623.135 minus that value, I'm going to get 180.163. And so if I wanted to report my final answer, the change in standard entropy is going to be 180.16 joules per Kelvin. Okay. And so for now, this value means absolutely nothing to us. The fact that it's positive and not negative, once again, exemplifies our prediction. It supports our prediction that overall the entropy is going to increase from reactants to products. Okay. So all of our conclusions are converging to the same point, which is what we want. And so if you guys are getting a negative value, then there's something that you did wrong in your calculation. And you guys can use this idea of predicting if entropy will increase or decrease, and as a tool, I apologize, as a tool to check your work. All right, so that's it for this video. I will we'll tie in enthalpy and entropy together, and we'll talk about spontaneity, which was the main point of this chapter. All right, catch you guys in the next lecture video. Bye.